Hi, welcome to my presentation. My name is Bill Lee, and this is on my first of 3 papers. So the first paper is called Chisel, Reshaping Queries to Trim Latency in Key Value Stores. It does sound like quite a mouthful and quite ambiguous at the moment, but we'll get straight into it, and you'll be pretty impressed like I was once you understand what's going on. So the authors, special shout out to Robert Birke, Juan F. Pérez, Sonia Ben Mokhtar, Navaneeth, Rameshan, Lydia, and Lydia Y. Chen. So this paper was part of the IEEE International Conference on Autonomic Computing, ICAC 2019. And in the bottom right there I have a picture of an actual chisel. But do not be afraid, this paper is not actually about that chisel. Reducing latency in key value stores. So the problem that this paper is trying to solve is to basically that title right there, reduce latency in key value stores. Now, to actually understand what that means, we have to break down latency and key value stores into what they mean in this context. So the latency is described by the duration that a request is made from the application or the client side through to the server and then back, the response is received back. Now, the key value store is a data store, and this is where data is stored, and what we're going to be referencing is a service called memcached. Now what memcached does is it stores data, it allows you to store data or information in memory, and another popular tool for that is something called Redis for other people out there. So now what that means is combining these definitions, there's clearly some situation here where an application is making a request, and then that request is hitting an in-memory cache, and then that information is being retrieved and returned to the application side, and this paper is looking for a way to reduce that time period basically as a whole. So why is this a problem? Why do we need to reduce latency in key value stores? So a great example in the paper is that the average number of keys in a single request at Facebook is 24. However, 10% of the requests made at Facebook on Facebook contain more than 100 keys, and that's basically a small number of requests consuming a lot of, basically taking the longest time to execute because of their large number of keys. So this paper has described this as elephant requests. So for reference, whenever elephant requests are mentioned, 100 these are requests with more than 100 keys, and basically this set of requests is considered the tail latency in the skewed distribution. Now that we've kind of defined what latency is, key value store is, and what the problem is, we look to the solution, and the paper has designed a solution which they've called Chisel, which I made a very bad reference picture at the beginning about. Anyhow, so in the original method, I should state, is just basically using memcached by itself, and that is basically already employing a kind of practice in application development where to actually cache the results of say you have like a MySQL database and you make a query and then you actually cache your results in memory. So memcached allows you to do that, and it helps speed up your application, because then subsequent requests for the same kind of data don't actually have to be sent all the way to disk. And the solution that so back to the solution itself now, which is Chisel. Chisel is basically a client-side solution that kind of helps better optimize or better utilize memcached. So yeah, I'll get into how that works. Right, so Chisel architecture. We'll start by defining the architecture of Chisel. Initially, I didn't really think how this could be related to the paper, the conference itself, and the whole idea of self-adaptive systems. However, once I kind of saw this diagram, it all kind of clicked for me. So the Chisel architecture is composed of an analyzer thread, a dispatcher thread, and a pool of query threads. And this diagram here shows how they basically interact. And Chisel sits on the client side, so it can be deployed to multiple clients simultaneously. And it's not dependent on anything to do with memcached other than the generic memcached like GET requests that you are required to utilize. How it works. So how Chisel works is it breaks down the bigger requests, these elephant requests, and it splits them into smaller ones which can be handled in parallel. So once again, going back, 10% of these requests contain more than 100 keys, as they can be split into requests which contain a lower amount of keys but can be processed in parallel. Then we've already seen an improvement in performance. It also combines smaller requests using techniques such as merging or batching. This is because, so for example, batching would be actually combining multiple keys within a single user request and sending them together, basically. A single user request can contain multiple queries that you want to be running, and it's quite faster to actually batch them and send them all at once than actually send them one by one independently. Merging is kind of different, where you have multiple requests and you find similarities between them, and then you basically just initiate one you just dispatch one, I guess, request or query to memcached for the result that's desired by that or by those requests. And the way that this paper evaluated the performance of Chisel was basically using identical servers, and they one with memcached on it and one with memcached and Chisel, and some integration tool that they've kind of created to actually make Chisel work for the test. So the baseline that they used is batching only. There's no splitting or merging of requests, and they can actually utilize the parallel queues. And performance-wise, they measure the performance using the amount of latency reduced from the baseline. So the baseline is basically just memcached without Chisel, and then they measure the performance of Chisel with memcached against just memcached. That's in short. So the conclusion of the paper was that the client-side solution that they had created, Chisel, was actually effective in reducing average and tail latency in situations which there was a skewed number of key value pairs. So that's pretty good. That's really good. So my critiques of this system introduced in this paper would just have to be around the practicality and the use cases kind of required by Chisel. So the example that was used in the paper was obviously Facebook. and that's kind of a well-established system with an architecture built on best practices, and so which means that it actually you can expect their servers to actually utilize in-memory storage using memcached or even Redis. However, that's not necessarily always going to be the case. That these memory systems are going to be used. In that kind of situation, this is probably not going to be very useful, as it kind of depends on optimizing and trimming queries for memory storage or these key value data stores. And also is the developmental cost of integrating it with an existing system. Is most applications are kind of sitting very comfortably, as the user only requires like 0.3 seconds to respond, and they won't notice anything. And so, like, really, how much faster do you need to go when the user's already okay with it? One thing that is quite curious about is there is an analyzer thread as part of the Chisel's design that does monitor the latency and tries. I think it might retrieve more data about how memcached operates, and I'm wondering whether that information is like secure and how much of it can be actually extracted strictly from the client side without introducing any backdoors to the server side. Yeah, that's about all I have. Thank you.